Hi, in this video we're going to talk about reactions in aqueous solutions. So in order to understand why particular sorts of reactions happen exclusively in aqueous solutions, we need to understand the nature of water. And specifically that water is what we call a polar molecule. Now if you're in my class, we haven't really talked much about molecules and polarity. That usually happens in Gen Chem 2, but if you're interested, you can get a preview. I'll drop a link to a video below. Essentially, what happens is because oxygen is very electronegative and hydrogen is not electronegative, you get polar bonds, and the whole molecule ends up being polar with a negative pole on the oxygen and a positive pole down on the hydrogen end of the molecule. So up till this point, when we've talked about charges on various things, we've been talking about ions where you have, let's say, NaCl, where chloride has a -1 charge and sodium has a +1 charge. These are really tiny charges in comparison. So for example, the charge on the oxygen molecule is about -0.1 and the charges on the hydrogen molecule are about plus 0.05. So these are very small charges relative to the charges we've been talking to up till now, but it still is a polar molecule. So this is a picture of one single water molecule, but water molecules rarely occur singly. They usually occur with a whole bunch of other water molecules. And what ends up happening is that you have these forces, these electrostatic attractions called hydrogen bonds that hold water together, where basically you're going to have the positively charged hydrogens of water attracted to the negatively charged oxygens of water. And while it's not as strong as, let's say, an ionic bond or a covalent bond, it definitely is a reasonably strong force. And that's why we can get things like water gliders and stuff that float on top of water. It's what we call water tension. So what does this mean for aqueous solutions? Well, aqueous solutions are really great for reactions that need charged particles to exist. So let's take a look at that. Basically, you have the small charges on water molecules helping to neutralize charges on ions. So in this case, we have a chloride ion in solution, and you can see what happens is the water molecules rotate so that the positively charged hydrogen end of the molecule is facing the negatively charged chloride ion. And so what happens, if you throw an ionic compound in water and it starts to dissolve, what's going to happen is that the ionic compound will actually come apart, with each of the ions undergoing a process that we call dissociation. So they're basically splitting apart from each other, and they're going to end up in solution. So in this case, the positively charged sodium ion now has negatively charged oxygens facing it, and the chloride ion again ends up with the positively charged hydrogen ions facing it. So dissociation is the process of something breaking into individual charged particles in aqueous solution. So oftentimes these are ionic compounds, but not always, as you will see later on. If you have a polyatomic ion, like let's say bicarbonate, that's going to stay as one unit. So the individual atoms within a polyatomic ion will stay together. They won't come apart in solution. So for example, if you have sodium chloride, as I said before, the sodium and the chloride will come apart. For every 1 mole of sodium chloride you have, you'll end up with 1 mole of sodium ions in solution and 1 mole of chloride ions in solution. And this works for other ions as well. If you have potassium bromide and you throw 1 mole of potassium bromide in solution, you'll end up with 1 mole of potassium ions in solution and 1 mole of bromide ions in solution. If you have 1 mole of sodium carbonate in solution, you're going to end up with 1 mole of carbonate ions, but you're going to end up with 2 moles of sodium ions because sodium carbonate is Na2CO3. One of the things about dissolving compounds in aqueous solutions is that we can get what we call electrolytes, which are basically solutes that enable a solution to conduct electricity. In order for electricity to be conducted, basically, somehow you're going to have to move electrical charges around. And so what you need is something that itself has a charge that will enable those electrical charges to move. So generally, when we're talking about electrolytes, we're talking about ionic compounds, but you also may be talking about acids or bases, although those tend to be much weaker electrolytes than ionic compounds. That means they don't conduct as much electricity. So now we're going to quick talk about an addendum to writing chemical equations. Prior to this, we talked about how a properly written chemical equation includes all of your reactants and products and the ratios in which they either react away or are formed, depending on which side of the equation you're on. But also, you need to talk about what form those reactants and products are in. So what do I mean by that? Basically, I'm referring to what we call state symbols. When you think about states of matter, you almost always think about solid, liquid, and gas, but we have here a fourth state symbol that we use quite a bit, which is aqueous, AQ. I'm pretty sure you know what solid, liquid, and gas are. Aqueous means dissolved in water. And so what we're going to do is we're going to write these after each of our reactants and products. So if you have a reaction where solid zinc reacts with an aqueous solution of hydrochloric acid to form aqueous zinc chloride and hydrogen gas, you're going to write it this way. So you can see here that we've got solid zinc, aqueous hydrochloric acid, aqueous zinc chloride, and gaseous hydrogen. Here's another example. Aqueous silver nitrate and aqueous sodium chloride combine to form solid silver chloride and aqueous sodium nitrate. Again, you can see by reading the description, everything here is aqueous except for one of our products, which is solid. For the rest of this chapter, we're going to talk about 3 different sorts of chemical reactions that happen in aqueous solution. The first one, which we're going to talk about in this video, is what we call acid-base neutralization reactions. The second one, which comes in the next video, is precipitation reactions. And finally, we're going to talk about my favorite sort of reactions, oxidation-reduction reactions, which we often shorten to redox reactions. So we're going to conclude this video by talking about acid-base neutralization reactions. What is an acid and what is a base? When you were in elementary school, you might have heard things like, oh, acids are sour, bases are bitter, and stuff like that. A chemical definition of an acid might be a substance that produces hydrogen ions in solution. So if you put it in aqueous solution, it's going to produce H+ ions. There are actually multiple definitions for acid. This is what we call the Arrhenius definition. There's also an Arrhenius definition for what a base is. A base is a substance that produces OH- in solution. So these are hydroxide ions that are characteristic of basic solutions. Now, if you put an acid and a base together, what ends up happening is that you get H+ ions from the acid and the hydroxide ions from the base combining to form liquid water. And this is why we call them neutralization reactions, because both the acid and the base disappear and form something innocuous, water. Now, a lot of times we will see acid-base neutralization reactions in the context of titrations. Titrations are a method that help us determine the concentration of one solution. So this is an unknown concentration, and we're going to do that by adding a measured amount of a different solution with a known concentration. Now, there are many ways to titrate, but you're only going to learn about one of them in this class, and that is an acid-base titration. In order to determine the molarity of an acid or the molarity of a base, what you're going to do is start off with a very precisely measured volume of that solution. And so what we're going to do is we're going to use a volumetric pipette to put a small, precisely known amount of that solution in some sort of glassware, usually a beaker or an Erlenmeyer flask. Here I've got a beaker of solution. And then we're going to use usually a burette, so a piece of glassware which can help us measure volumes very precisely. And we're going to add that solution to our unknown a little bit at a time until what? Until our H plus concentration equals our OH minus concentration. And this can be signaled in a number of ways, but the way that is usually used in introductory titrations at least is some sort of indicator that changes the color of the solution. But just because you've reached that color change does not mean that you automatically know what the concentration of the solution is. What you have to do first is some stoichiometry. Here's an example. Let's say we had some hydrochloric acid, and aside from knowing it was HCl, we don't know what the actual concentration is, but we're going to take a 10 mil volumetric pipette, so this is very precise glassware that will give us exactly 10.00 milliliters of sample. We're going to titrate it with some NaOH that we know is 0.1997 molar. And then we're going to keep adding NaOH to it, and at the end, when we reach that equivalence point where our indicator changes color, we have added 22.89 milliliters of NaOH. So we want to know what the molarity of the HCl is, and you have to ask yourself when you're doing these problems, what is molarity? Well, the molarity of the HCl is going to be the number of moles of HCl divided by the volume of HCl in liters. Do we know either of these numbers? Well, right now we know the volume of HCl in milliliters, which we can of course convert to liters pretty easily. So how do we calculate the moles of HCl? Well, we may not know the moles of HCl, but if you look here, we've got the molarity of NaOH and a volume of NaOH, and that will give us moles of NaOH. And then all we need to do to figure out how many moles of HCl we have is think about our mole ratio. So let's write a balanced equation for what's happening as we titrate. And basically, we're having aqueous HCl plus aqueous NaOH forming aqueous sodium chloride and liquid water. If you're not sure exactly what's happening in a titration, it's helpful to write what we call an ionic equation, which is something we're talking about in the next video. So after you watch that video, you might want to come back and write out the ionic equation for that as well. And then you will easily be able to come up with the molecular equation that I show here. So you can see in this particular one, all of our coefficients are 1. So that means we have mole ratio of 1 to 1. And now let's use that information to determine how many moles of HCl we have. So we're starting with 22.89 milliliters of NaOH, and I have converted that to 0.02289 liters of NaOH. We're going to multiply that by the molarity. Remember, molarity times volume equals the number of moles. So we have 0.1997 moles of NaOH per liter of NaOH. Then we're going to multiply by our mole ratio, and you can check your units here, and you see that we do end up with moles of HCl. And the number I get when I put that into my calculator is 0.004571 moles of HCl. So now let's take that number of moles of HCl and let's plug that into our molarity equation. So we're going to get that number of moles of HCl, of course, divided by our 10 milliliters, which is 0.01 liters. And so we get 0.4571 molar HCl.